In the organic chemistry, hydrocarbons are divided into two categories: saturated hydrocarbon and unsaturated hydrocarbon. In the saturated hydrocarbon, we have already discussed alkanes. In the category of unsaturated hydrocarbon, alkenes, dienes, alkynes are discussed. As the name suggests, dienes are the hydrocarbon with two double bonds. In this lecture, we will be discussing about their nomenclature and classification. Since conjugated diene is the most important class of diene, their structure and isomerism will be discussed in detail. Methods of preparation and reactions of 1,3 conjugated diene will also be covered. And finally, applications of products of polymerization of diene will also be discussed. Now, as the name suggests, these are simplest of all polyenes. Some of the important naturally occurring polyenes are limonene and myrcene. These are basically responsible for the fragrance of lemon and orange and oil of bayberry. Lycopene, another important naturally occurring polyene, is found in ripe tomatoes and watermelon. But overall, most of the acyclic dienes are synthetic ones. General formula of the dienes is same as that of alkynes, that is CnH2n-2. Here we can see the example of 1,2-propadiene, which is having two double bonds at adjacent position. Another example, here double bonds are separated by one single bond. Now, coming to the nomenclature, we can see here double bond is present between C1 and C2, and hence this prefix 1. Another double bond is between C2 and C3, and hence this prefix 2. So, after 1, 2 we will add propa. Propa means 3 carbon atom. Diene means 2 double bonds. Another example, we can see a methyl substituent is present at C2. So, we will prefix 2 methyl, and then again for C1 and C2 double bond we will put prefix 1, and for C3 and C4 double bond we will put only 3, and then there are total 4 carbon atoms in a straight chain of carbon atoms. So, the name 2-methyl-1,3-butadiene. Dienes can be classified into 3 important categories. Simplest of those are the isolated diene. Isolated diene, as the name suggests, here double bonds are separated by at least 2 carbon-carbon single bond. In another example, double bonds are separated by 3 carbon-carbon single bond. Here also we can see their nomenclature, 1 for this and then 4 for the second double bond, and then there are total 5 carbon atom, and hence the name will be 1,4-pentadiene. Second category of the diene is the cumulated diene. Cumulated diene means when double bonds are present on adjacent positions. They are commonly known as allene. They are very important in stereochemistry because their substituted derivatives here, if we substitute both of the hydrogen atoms, and here also if we substitute these 2 hydrogen atoms by some bulkier groups, we will be getting a compound which will be non-superimposable over its mirror image. Hence, it will be asymmetric. Therefore, substituted allenes will be optically active. Third important category of the diene, which is most important, is the category of conjugated diene. Here, as the name suggests, double bonds are alternate position. So, here we can see C2C3 will be the single bond. In the second example, again double bonds are present at alternate position. C2C3 is the carbon-carbon single bond. Structure and stability of 1,3-butadiene. 1,3-butadiene is the most simple example of conjugated diene. Here we can see that every carbon atom is having a pi bond. C2 is also having this pi bond, C3 is having this pi bond, and C4 is also having this pi bond. Therefore, because of the presence of one pi orbital on each carbon atom will be sp2 hybridized. Therefore, on every carbon atom there will be a unhybrid p orbital. We can further understand structure of 1,3-butadiene with the help of this orbital diagram. Here we can see that all the unhybrid p orbital lie in a parallel way. Therefore, between C1 and C2 there is a pi bond formation. Here we can see from the line diagram also bond length is 1.34 angstrom, which is the bond length for the carbon-carbon double bond. In case of C3 and C4, here also due to overlap, sidewise overlap, a pi bond is formed and therefore second carbon-carbon double bond is here. But here it is observed that C2C3, it does not remain a true carbon-carbon single bond. True carbon-carbon single bond should have the bond length of 1.54 angstrom, but here we can see bond length is 1.48 angstrom. This is shorter than what would we expect. So, we can see that partial double bond character has been there. Why? This character has been developed due to small amount of overlap between C2 and C3, since p orbitals are lying in the parallel manner. Because of this delocalization of pi orbital, what happens? 1,3 conjugated dienes are extra stable and therefore they will be preferred product of elimination. Here we can see from the value of heat of hydrogenation also. This is the saturated hydrocarbon pentane. This is again same saturated hydrocarbon pentane. This is isolated diene and this is the conjugated diene. When isolated diene is hydrogenated, then more energy is released and finally it is being converted to the same molecule as here, but here amount of energy released in the hydrogenation is less. So, it clearly indicates that isolated diene is less stable than the conjugated diene. Conjugated dienes show stereoisomerism. Stereoisomerism means isomerism due to difference in orientation in space. So, 3 stereoisomers are possible for the 1,3 dienes with alkyl groups present on the terminal carbon. Here we can see this example of EE13 diene, means trans-trans 1,3 diene. So, there are 3 stereoisomers possible: trans-trans, cis-cis and cis-trans 1,3 diene. Here we can understand that one hydrogen atom will lie in this direction and one hydrogen atom will lie in opposite direction. So, therefore, bond will be trans. Now, we will see second carbon-carbon double bond. Hydrogen atom will lie in this direction and again hydrogen atom will lie in opposite direction. So, this carbon-carbon double bond is also trans. So, this compound is known as trans-trans isomer. Now, second example, we can see both of the hydrogen atom lie on the same side of carbon-carbon double bond. So, therefore, bond will be cis. Here also both are cis position. So, this compound is cis-cis 1,3 diene. Now, coming to third stereoisomer, both of the hydrogen atom on the same side means cis and hydrogen atoms on opposite side means trans. So, this is the third cis-trans 1,3-diene. Two possible conformations result from rotation around the carbon-carbon single bond that joins the two double bond. Here we can see this carbon-carbon single bond can freely rotate to give another isomer. This form is called S-cis conformer and this is called S-trans conformer. We know from our knowledge of stereochemistry that conformational isomerism is the isomerism shown due to free rotation around the carbon-carbon single bond. But conformer are not separate identity, they are interconvertible. So, we can see these two are stereoisomers, means configurational stereoisomers which are separate identity cis-cis and trans-trans, but this trans-trans can be converted to another same trans-trans isomer, but only difference in the conformation. So, these two are conformational isomers. Now, coming to the methods of preparation of conjugated diene, we will be taking example of simplest diene, that is 1,3-butadiene. This can be prepared by the dehydration of 1,4-butane diol. We can see here that OH group is present at carbon number 1 and carbon number 4. So, after dehydration, H and OH will be removed from here and H and OH will be removed from here. So, 2 moles of water will be taken out in the presence of P2O5 or sulfuric acid and 2 new double bonds are generated. In another method, we can see that butane 1,3-diol N steam is passed over trisodium phosphate containing 20% phosphoric acid. Here again dehydration takes place across these two and these two, and hence 2 double bonds are generated at respective positions. In another method, dehydrohalogenation of 1,4-dichlorobutane is done with the help of alcoholic sodium hydroxide. Here we can see hydrogen atom and chlorine atom, they are being eliminated from here, and one chlorine atom and hydrogen atom are being eliminated from here. So, we are taking out 2 moles of HCl and we are getting 1,3-butadiene. From acetylene and formaldehyde also we can prepare the conjugated butadiene. Here we can see the acetylene molecule which is having carbon-carbon triple bond. So, these 2 hydrogen atoms are being substituted by this group and this group is being converted to CH2OH in the presence of cuprous acetylide. And after hydrogenation in presence of nickel, we are getting saturated compound of butane 1,4-diol. Hydrogen is being added across this carbon-carbon triple bond and here we are getting the saturated compound. After that, as we did in the earlier method, 2 moles of water will be removed and we will be getting 1,3-butadiene. Pyrolysis of cycloalkene. This is another important method. This is basically reverse of the Diels-Alder reaction. Diels-Alder reaction when these two compounds combine with each other to give this cycloalkene. So, in this reverse reaction, in the presence of nichrome alloy, here carbon-carbon bond is broken and here also carbon-carbon bond is broken and we will get conjugated diene and an alkene. In industrial preparation, cracking of hydrocarbon is done in the presence of heat and catalyst and we get 1 butene and 2 butene. If this process is continued, then in the presence of same catalyst and at high temperature, we will be getting 1,3 butadiene. After discussing methods of preparation of conjugated diene, we will start reactions of conjugated diene. Most important reaction of conjugated diene is addition reaction. This may occur through two ways. First is the electrophilic addition and second is the free radical addition. At low temperature, 1,2 addition product is the major product, which is also known as kinetic product because it is formed at a faster rate. Here we can see that hydrogen bromide is being added to 1,3-butadiene. Across this double bond it is being added and therefore 1,2 addition product is formed in the 80% yield and only 20% yield of 1,4 addition product is being formed. But same reaction if we perform at high temperature, major product of this reaction is 1,4 addition product. Here we can see that HBr is being added across C1 and C4 carbon atom. Here we can see 85% yield of C1 and C4 addition we are getting. This product is called thermodynamic product because it is thermodynamically more stable. To understand formation of thermodynamic and kinetic product, we will have to understand mechanism of the reaction in much more detail. Here we can see formation of two type of product 1,2 and 1,4. First of all, HBr is undergoing heterolytic fission and we are getting H plus electrophile. This being positively charged will attack on electron rich double bond. So, therefore, electrophilic addition reaction starts and this H plus is being added here and C plus is generated here. So, this is allylic carbocation. This can be converted to another form of allylic carbocation where carbon plus is here due to movement of this pi bond from here to here. But since this allylic carbocation is more stable, as we can see from here, this positively charged bearing carbon atom is being substituted from plus I effect group. Therefore, this is much more stable in comparison of this allylic carbocation where there is no electron donating substituent present. Therefore, at low temperature, rate of formation of 1,2 addition product will be very fast and we will be getting 1,2 addition product as a major product. But at high temperature, when energy of activation can be obtained, here we can further understand with the help of this diagram. Here we can see this is the conjugated diene. This is being attacked by HBr or HCl, any unsymmetrical reagent, and we are getting 1,2 addition product kinetic one and 1,4 addition product thermodynamic one. But from this energy diagram we can see that for the formation of kinetic product, energy of activation required is less. Therefore, at low temperature this is easily being converted to the kinetic product, but this product is less stable than the thermodynamic one. So, at a higher temperature what happens? Rate of formation of this kinetic product is increased, but in the same time rate of decomposition of this kinetic product is also increased. So, it will revert back to this allylic carbocation and here it will get the extra energy of activation required to cross this barrier and then it will be finally converted to the much more stable thermodynamic 1,4 addition product. In another type of addition reaction which is from the free radical addition mechanism, we can see again HBr is being added to the 1,3-butadiene. It will undergo homolytic fission and it will generate free radical of hydrogen and bromine, and here we will be getting allylic free radical here and another resonance stabilized allylic free radical here. So, this is the resonance stabilized allylic free radical, and via these two different intermediates we will be getting two different products. One is 1,2 addition product and another is 1,4 addition product. It has been observed that in the free radical mechanism 1,4 addition product is the much more formed product. Second reaction is polymerization reaction, which is very important reaction as far as commercial significance of 1,3-butadiene is concerned. In the presence of catalyst peroxide, we will be getting polymerization of 1,3-butadiene and polybutadiene is being formed. Polybutadiene is also known as Buna rubber. Bu stands for butadiene and Na stands for sodium. We will understand this clearly from the mechanism of this reaction. Polymerization of dienes can occur both by 1,2 and 1,4, but mostly 1,4 addition is dominated. Again in the 1,4 addition there are two possibilities. We can get cis addition or we can get trans addition, but again later mode is the preferred one. Mechanism of this reaction we can understand. First of all, peroxide will be broken into free radical and then this peroxide will be attacking the single unit of butadiene, converting it to the free radical. So, this is the initiation step. In the second step, which is called propagation step, this free radical will attack on another molecule of butadiene and in the same way this will be continued. So, we will be getting a long chain of free radical. Finally, termination step takes place when different chains of free radicals will be combining together to give us polybutadiene. Polymerization gives us various type of polymers. Homopolymers are very simple, as here repeating unit is the only single molecule. Natural rubber is the polymer of isoprene. Isoprene is derivative of 1,3-butadiene. Natural rubber has got cis stereochemistry. We can see here at 2 position it is methyl substituent. This side is known as head and this side is known as tail. So, we can see how tail is being attached to the head, and in the same way this addition will be continued and finally we will be getting cis form of the polyisoprene. Why it is called cis? We can see here across this double bond smaller groups are methyl and hydrogen and these two groups are on the same side of the double bond. So, this is cis. Now, synthetic rubber, which is also known as gatta parcha, it is polymer of isoprene with all trans configuration. Here we can see again same isoprene is being added to another unit of isoprene. This is also homopolymer, same repeating unit throughout, but here addition is taking place in the trans manner. We can see across this double bond smaller group is methyl, which is here on one side of the double bond, and here another smaller group H is on the other side of the double bond. So, this is trans configuration and this is synthetic rubber. Superior quality rubber is the neoprene, which is polymer of chloroprene. Chloroprene, there is a slight difference between isoprene and chloroprene. Here in the isoprene CH3 group is present at this position. We have substituted CH3 by Cl. So, monomeric unit is chloroprene, which is also known as 2-chloro-1,3-butadiene. in the presence of peroxide, as we are progressing our reaction through free radical mechanism, we will be getting polychloroprene, which is commonly known as neoprene. Neoprene is a very superior quality rubber. As we can see, this is very important substitute for natural rubber, as it is resistant to heat, oil, gasoline and many other organic solvents. Superior quality tires are obtained from this quality of rubber only. This is also used for the preparation of conveyor belts, printing rollers, rubber cement and laptop covers. Now, most of the polymerization reaction we have so far understood, we are following the free radical mechanism. Now, if we want to control the stereochemistry of the product, another type of polymerization reaction is followed, which is known as coordination polymerization. Ziegler and Netta, two scientists, got Nobel Prize in Chemistry in 1963 for their work on a catalyst. In this catalyst, they were able to control the stereochemistry of the polymers. In this catalyst, there were two parts, one is catalyst and other is co-catalyst. Catalyst was the halide of transition elements, for example, titanium trichloride, and in the co-catalyst, alkyl and aryl derivatives of the elements of group 1 to 4th were used. So, these two compounds in combination form a complex and then this complex become attached to the monomeric unit, and then they were able to control the stereochemistry of the product. Copolymer. Copolymer, when more than one monomeric unit is being involved. Here we can see 1,3-butadiene is being combined to the styrene, and then after combination this is being formed. Then this unit is being repeated throughout and we will be getting the final polymer, which is known as BUNA-S. Bu for butadiene, Na for the sodium and S for the styrene. It is also known as sodium styrene butadiene rubber. BUNA-S, this is also very important from the commercial point of view, as it has been used for the manufacture of tires, rubber soles, waterproof shoes. This is also used for the production of wires, cables and insulators, but it is not resistant to oil and solvents. BUNA-N, another important polymer obtained from 1,3-butadiene. We can see this is also copolymer obtained from two monomeric unit. One is 1,3-butadiene and another is acrylonitrile, and hence N stands for the nitrile. It is much more useful than BUNA-S as it is resistant to organic solvent. It is used in the fuel tanks, high altitude aircraft components, gaskets, adhesives, automobile parts, oil resistant foams, etc. Another very important topic which needs to be discussed here is vulcanization of rubber. Properties of rubber can be improved by a process called vulcanization. In this process, rubber is heated with sulfur, and because of this, sulfur forms crosslinks between various chains of polymers. We can further understand with this example. This is one chain of the polymer and this is another chain of the polymer. When it is being treated with sulfur at high temperature, cross-linking between the chain at various position through sulfur atom is taking place. Due to this cross-linking, this rubber becomes hard and strong. So, strength of the rubber can be improved by adding sulfur at temperature. It is the percentage of sulfur and temperature which will govern the strength of rubber then formed. These cross links will make the rubber very hard. Since independent chains are now locked together to form a giant single molecule. Reactions of conjugated diene. Now we will be discussing very important reaction of organic chemistry, which is the Diels-Alder reaction. This is basically 4 plus 2 cycloaddition reaction. 4 stands for 4 pi electrons coming from the butadiene side and 2 stands for 2 pi electrons coming from the alkene. This alkene is called here dienophile and a adduct is being formed. This reaction does not involve any ionic or free radical mechanism. It is basically concerted reaction, single step reaction, where it is proceeding through a transition state, and in a single step these two carbon atoms are being joined and these two carbon atoms are being joined. Stereochemistry of the dienophile has been retained. We can see from this example, carbon is being joined to here and here carbon is being joined to here. So, if we are using the cis form of the alkene, then we will be getting cis adduct, and if we are using trans form of the alkene, then we will be getting trans adduct. So, we can see stereochemistry of the adduct has been retained. So, now we have discussed all reactions of dienes and uses of the many important products formed thereafter. So, in this episode we have discussed classification of diene, nomenclature and structure of diene, stereoisomerism of conjugated diene was also covered. We have also learnt methods of the preparation of 1,3 conjugated diene, its industrial preparation, reactions of 1,3 conjugated diene, addition reaction, polymerization reaction and Diels-Alder reaction were also discussed. So, at the end we can see that conjugated diene is the very important compound of the class of dienes. Its commercial significance lies in its products like rubber, synthetic rubber and many important derivatives which are used for the preparation of important polymers. For example, isoprene, chloroprene which are being used for the preparation of many important polymers. Thank you.